Is it on? Yes? Okay, thank you.
So let's go for the last talk of this morning. So it's a talk by Fernando Garcia. He will talk about the disordered double perovskite, barium, titanium 1/2, manganese 1/2, oxygen 3 as a new spin liquid candidate, results from heat capacity and a spin resonance experiment.
Okay, thank you, Carol, for the introduction. And as usual, I'd like to thank the organizers for putting together this conference and as well to invite me over so we can discuss this data with a broader audience, I mean, with the community. This talk is about presenting our title compound here as a new spin liquid candidate. And I hope that by the end of the talk, I will actually convince you I don't hope that I will convince you that this compound hosts a spin liquid ground state, but at least that is something that is really worth take a look at, and I will present experimental evidence that it might be at least a spin liquid candidate, right? I'm really aware that I still have a long way to go in order to actually, in order to make the assertion that spin liquid ground state is here. But I think that we have very solid experimental evidence that this might be the case. So I'm not alone here. So, I'm doing this work with some long-term collaborators, including here Raimundo Serrano, who is at the Federal University at Uberlândia. He's actually responsible for making the samples. I have here Rafael Freitas, who is my colleague in my home institute here at the University of São Paulo. He's helped us with magnetic properties and specific heat. And this talk concerns most this paper, which is recently posted, not so recent, but a few months ago posted in the archives, which is essentially the master's work of my student Marli Cantarino, who is not here essentially because she is enjoying her exchange in Uppsala in Sweden. Right, and for this specific work here, I have the extra help of one of our organizers, like Erika Andrade, who is not responsible for our weakness and failures. He's responsible only for the strength, right? So of the paper, and I had the help of Professor Klaus Group at the Technical University in Dresden, who helped us with the MEOSAR measurements that we did on the PSI in Willigen. So this work relates to a previous work of our group, which is deal with magnetic dimmers and trimmers in this same title compound, and this is almost 3 years old. So we'll be talking a little bit about the results of this paper as a way to introduce you to the system, and then I will present new data. So here's an outline of the talk. I will start talking about the structure, as you can see here, just in this figure. It's a rather complicated structure, and I hope I can, at least explain the main features, explain the features that we believe that are important to understand the magnetism in this compound. And then I will turn to the subject of the magnetic dimmers and trimmers, which we now understand as part of the high temperature magnetic properties of the system, right? And later on, it will become clear that after we understand that, there will be an obvious and open question, which is what happened to the system at further lower temperatures, and that I will turn to the last part of the talk, which essentially I will discuss the heat capacity and MEOSAR data, and here is more or less what we get at the end, right? So let's begin with the structure. So here it is. As I said, it's a rather complicated structure. What we are seeing here is this structure is built on a hexagonal lattice, so it's kind of a low symmetry. It's a low symmetry perovskite, and here you have like two distinct barium sites, two distinct oxygen sites. But what I really want to call attention is for this set here of transition metal sites. We have 3 transition metal sites, and we have here this, what I can call a structural trimmer. Here we have like M2, M1, and M2 sites. And I have this other one here, which are corner-sharing octahedra here, and this sharing octahedra actually connects the distinct structural trimmers, right? So if I take a look at the transition metal sites, what I will observe here is that I have this M1 site at the center, M2 bordering the center, and the trimmers are connected by this guy here. So our proposal for the structure, which is actually not really ours, it was thought before. We were just verifying that with different techniques. But the current understanding about the structure is that the M3 site is exclusively occupied by titanium cations. The M1 site here, sorry by this arrow, the M1 site is here, and this is occupied exclusively by manganese 4+ cations. And you have the M2 site, which has this mixed occupants. And then I say this is a disordered double perovskite. I'm talking about this mixed occupants here of this M2 site. So as you can see in this proposal, all the manganese cations are within these structural trimmers. So all magnetic properties comes from these structural trimmers. You have, like say, you should expect a very strong first neighbor interaction here, you know, but the trimmers will talk to each other only by means of this exchange path here or by direct exchange. I mean, but of course that you expect something like a very strong interaction here, and if you think about how this interaction will go to the whole compound, actually this is they will talk through that, and this will be kind of a weak interaction. So we expect somehow at least 2 energy scales, and that will be important. So that's what we are seeing here, that the trimmers are what, in a sense, at least at high temperatures, magnetically isolated. And the idea here is that if you simply work out the stoichiometry, you have like, okay, so if this is exclusively occupied by manganese, this is exclusively occupied by titanium, the mixed occupancy here should be really half-half. So you have like half the sites are occupied by titanium, half the sites are occupied by manganese. This is the way that this should be this way, so you can keep the stoichiometry right. There is no other way to do it, right? And here we just by charge, if you do the charge balance, you think that it's manganese 4+, and that I will now resort to some experimental results trying to support this scenario. The first thing I do is try to verify the valence. So for that, we simply do XAS, right, X-ray absorption. And here you can see how the spectrum for our compound here nicely correlates with the spectrum for the standard for manganese 4+, and here the comparison with some other valence here. And so I think that, in terms of our sample, this will go down to say that we have negligible oxygen vacance, because otherwise we have charge distribution, and then you could have some sort of mixed valence. And we have as well that this is like a spin 3/2 systems, right? We have local moments S equal 3/2. So this is, like say, the first message we got. The other thing supporting our structure, neutron diffraction measurements. It is the result of recent heat field refinement. We can discuss later. We have some other data stuff. And this is as well what we did do with X-ray diffraction. But one of the main problems that from the point of view of both neutrons and X-rays, titanium and manganese are actually, they look very much the same, right? It's very hard to distinguish the occupation because of coherence scattering length. So what you do, you try to do X-ray in a little bit more smart way. You simply change the energy close to the absorption edge of the manganese, for instance, and that gives you what we call anomalous diffraction. Essentially, since you are close to the absorption edge, the intensity will be anomalous large, right? So you can distinguish the reflections that comes from due to structure, due to manganese or titanium, and so on. This is a way to try to distinguish a little bit. And then we test our model, and systematically what always gives you the best statistics, the best fittings that you can get from the Rietveld refinement is this proposal, right? We are doing pretty much the same thing with XAFs, right? And we always get something which supports the idea of that mixed occupation. That's the best you can do. You know, it's something that that's the best we can do for now. So if you believe that we have this structure, we start to think about the magnetic properties. So here is a really broad overview in this temperature region of the susceptibility. And what called our attention at first time, this huge drop here in the susceptibility, and we could not observe this is field cooling, zero field cooling. We saw no hysteresis and no other sign for phase transition. At this temperature, at least, you cannot actually miss a phase transition, right? So we simply start talking, okay, what is happening here? And from a phenomenological point of view, we resort to this O2 population model. And what is this model telling us is that you have, like, say, two populations of spins in your system. At high temperature, you will cover the effective moments from manganese 4+ cations, what you actually expect. And at low temperature, apparently you have some spins which are somehow correlated, right? And then if you look again at the neutron scattering data at low temperature, you see that you have no additional features here that would appear if you had a magnetic order state, right? So you have this drop here, susceptibility, and whatever, and here you have no sign for phase transition. That's pretty much the same with the heat capacity that we had at that moment, and so on. So after doing that, we went back to the structure and started to think a little bit more about, as I said, that all magnetism should stand from this streamers, and then we went back to the structure to see, in order to get a better view of what was happening. And that come along this idea of the dimmers and trimmers. Now I'm talking about magnetic dimmers and trimmers. So since all manganese cations are side trimmers, and if you work around the possible occupations, what you have something like, you can have either, let's say, isolated manganese spin, which we can call an orphan. You can have a dimmer, meaning this kind of occupation here, and then you can model like that. And you can have a trimmer like this one, right, which we can model like that. So if you try to describe the susceptibility in this way, this is more or less what you would get. So these are the possible things that you get, and try to describe this, the magnetism at high energy, right? So okay, so let's go here. So actually, you could believe that when I talk about the trimmer, you would expect this guy here to be much larger than the second neighbor interaction. But if you think it through, we have reasons that this is not really the case. Actually, if you use that, you cannot reproduce experimental data. You have a lot of exchange paths here, and we kind of think that this is the reason that these guys are actually kind of comparable. And they need to be comparable in order to introduce some sort of frustration in the system that will lower the magnetic response, and the magnetic response become more or less compatible with what we get from experiments, right? So we did that, and this is kind of the results we got, right? So this is, like, say, just try to understand what are, in a very broad view, what is the magnetism at high temperature. So of course, when you see that, it raises immediately the question that we are fitting here just up to this, not down to Kelvin, because we know now that if you measure the susceptibility, let's say, down to 0.4, you start seeing the sign that this guy is not anymore a simple paramagnet, but you can see some sort of sign of correlation here. And by correlation, I mean that, the susceptibility is flattening as you go down in temperature. So actually, it poses the question, what will happen to the system at further lower temperature, right? Because it's, if we look back at what we are saying, is essentially that at high temperature, you know, the spins, some of the spins will form dimmers. They will be frozen, right? They will not contribute anymore to magnetism. The NXK is pretty high. Then you go to a little bit to lower temperature, and then you still have the trimmers, that the ground state of the trimmers will contribute with an effective spin 1/2, and you still have the orphans, right? So you still have a lot of magnetism in the system. So essentially, this is the question that should be answered, and then we start investigating that. Okay, so the first thing that we did, and we thought it would be important, is essentially start counting and to see which are the remaining magnetic degrees of freedom. So if I go back to my unit cell and do this counting very carefully, because usually you can do some mistakes in this basic stuff, and then you realize that out of all that manganese, you have like the manganese, half the manganese will be participating in the formation of trimmers, 1/3 of the manganese will be part of dimmers, and 1/6 be orphans. These guys here are completely out, right? They do not contribute anymore to magnetism. Then for each mole of manganese, you have like 1/6 moles of effective spins 1/2, because like if I have 3/6 trimmers, for each mole trimmer, I have like 1/3 moles of effective spins 1/2, and plus 1/6 S equal 3/2 spins from the orphans. So these are the remaining magnetic degrees of freedom, and these are the degrees of freedom that are responsible for the magnetic response at lower temperature. So we decide to test this idea, and we fit the susceptibility down here with a simple Curie-Weiss behavior, just to see if the numbers turns out to be at least reasonable. So we get something like an energy scale for the interaction, which is minus 8.5, and we get a population of orphan trimmers, which is about 0.19 as expressed by the Curie constant here, and this should be compared with this number. This is the number which is expected if you're right. Okay, if you simply count the thing and calculate the effective spin. So the idea is, let's say, phenomenologically qualitatively correct. So we will take this as the effective degrees of freedom that we have. So if we do that, what we realize that this very complex structure that we have at high temperature, it will actually can be, let's say, mapped in a new structure, taking into account only the magnetic degrees of freedom. That's what we are calling the emerging magnetic lattice, meaning you stop thinking about all the degrees of freedom which are frozen, because they form dimmers, trimmers, and so on, and then you keep thinking only about this stuff here. So if you go back to structure and investigate that very carefully, what you see is that you have these bilayers of triangular lattice. They are somehow in an A-B stacking, and have these parameters here, and you have like a lattice of S equal 3/2 spins, and they are interacting with a lattice of effective S equal 1/2 spins. And these bilayers are pretty much isolated, right? Because they are really far from each other. If you go to the next bilayer, it's like up to I think 18 angstroms apart. So this is, let's say, the idea, right? We have like these bilayers here, and the magnetism comes from that. So then okay, this is nice, but what about the low temperature properties, right? So this is like the results from heat capacity. We turn out like kind of a new subject. So this is the heat capacity. We can see here measure up to 100, and these are, let's say, the main features are, you see this bump here in the heat capacity taking place here around 3 Kelvin. This is really field dependent. And then when you go down, you start to see an upturn here that could be due to a phase transition. And I try to convince you that this is not due to a phase transition, right? So I will try to convince you by showing at least 2 other possibilities. And this is the magnetic specific heat capacity that we get after subtraction of the phonon contribution. And as you see here, it looks like as it goes linearly to zero temperature, but that's not the case, right? When you fit, you get a different scenario, right? But I just want to show here, this is the bump, and it turns out that, you know, like when you increase the field, you displace that to a little bit higher temperature. So concerning this upturn here that I was talking about, actually, if you compare our specific heat at zero field that we can measure down to 50 millikelvin, we compare that with a magnetic, with the nuclear heat capacity, well, which was measured for another compound. Of course, that from a spectroscopic point of view, this guy is very different from this guy, but insofar as specific heat is concerned, it's not so different, right? Because electron field gradients and so on will not give, of course, in NMR you can see a difference, but not on thermodynamics. So here, as you can see here, it fits very well. It actually, you know, unexpectedly well. And it's apparently at the RD that this upturn here is actually due to the nuclear heat capacity. And I will show later another idea why we don't have, I mean, the MIOSAR results gives us that you don't have a order state, right? So, then that being said, I turn to the analysis of the heat capacity data. This is, I just come here and I feed a power law behavior. And as you can see here, this the alpha exponent, I would say it's pretty much constant, right, within the error bars, and it's a little bit, the average here is about 1.4 if you do the calculation. And this gamma exponent here, this gamma factor here, is even if you consider the error bar, is decreasing as you increase the field. And if you accept the idea that you have some sort of dynamic magnetism here, it can be understood as if, let's say, as you increase the field, you quench the fluctuation, then you decrease the contribution to the heat capacity. And here I will count, right? That's what I'm doing here. I'm calculating the entropy, and essentially I'm counting how many spins I still have in the system. And I got this number, which can be thought, okay, but that's way too small. But I must remember that this number must be compared with the remaining magnetic degrees of freedom, not with all the spins, right? As I said, I have only a few spins that still contribute to magnetism. The other spins are frozen, essentially. Their entropy was recovered at much higher temperature. And that, anyway, we still have entropy in the system, right? We can account only for 2/3 of the entropy. So, of course, that I still need to say something about you know, when we talk about the spin liquid, it's not, you have to go with microscopic and thermodynamic properties, so that we resort to MIOSAR measurements. Here I'm showing the kind of measurements that we got from the high temperature sector. We have measurements up to 150 Kelvin here, and this is how the spectra looks like for the high temperature stuff. And here, as you can see, the low temperature below 1.5 Kelvin, we can almost fit it with a single exponential, as it is reflected here with the fact that the parameters that you extract becomes essentially a constant, right? And this here, GPS, LTF, are two different spectrometers. You know, you have to change the spectrometer, but you take some points for superposition. So if you have some sort of order state, you would expect oscillations here in the muon decay, right? But here we don't see oscillations. You see something which simply decreases monotonically, and therefore there is no order state in this temperature range, and there is no indication for an order state or some sort of quasi-static magnetism at this temperature range here. And what you see is that if I simply measure the relaxation rate, you have something which is pretty much constant at high T, and then it goes through a really step increase and it flattens again. And if you take this region here, it's precisely the same region that you observe the bump in heat capacity. So I think this illustrates quite nicely relation between macroscopic measurements and microscopic measurements. So something's going on here, and we believe this is exactly a crossover, as we said. The same goes for the extraction exponential coefficient. It's certainly about 1 here at high temperature, and then it goes down, but it's really above what you would expect, like say 1/3 for a glass state, etc. But it's about 0.5 here, and furthermore, we actually sit at 20 millikelvin, and we ask, okay, but if we have some sort of quasi-static magnetism, and if we put, like say, if you apply a really small field, you would expect this to be able to quench this quasi-static fluctuation, and then you would expect something which is comparable to the theory here. And what you get is that you're still not able to decouple the experiment as we usually talk about. So we have evidence that we still have dynamic magnetism down to 9 millikelvin, but this dynamic magnetism is not simply it comes from a steep increase of this relaxation rate here, which in turn, if I if I extract from my data the field, the frequency of the fluctuating fields, we see that at high temperature have something that extend to the 10 hertz, and here at low temperature, which we extract from this fit, it's about 10 to the 6. So we have, like say, a full order of magnitude decrease in the speed of the fluctuation. And this is usually interpreted as a sign for formation of disentangled states that you should have in spin liquid state. So just to finish the talk, I think that what we just presents that certainly this guy here, our guy, presents a dynamic and correlated magnetic ground state. Fortunately, when I say ground state, but some entropy is still in the system, clearly. And we conclude that based upon a heat capacity. There is no phase transition down to this temperature. There is no static magnetism. But there is certainly a slowing down the fluctuations at about the same region. There is what we call crossover is observed in heat capacity. And furthermore, we can, as we said, we can correlate that with the population that we believe is still there in magnetic heat capacity, and we have an idea for the kind of emergent lattice that we have. And I think that the main perspective here is that we just came by, I think that last week, we were able actually to grow single crystals, right? Raimundo got it, my collaborator got it, and I was supposed to show you a video, but all the time I think that the video doesn't work. It did work for her, but probably will not work for me, so I decided just to show you a picture. This is like say the inside of the lamp furnace, and the video was supposed to show the exact moment where the seeds collapse and create a single crystal, but it's kind of captured here in the photo, and you guys can use your imagination. Okay, so thank you.
Thanks, Fernando. Other questions, comments?
So what are the expected couplings between these remaining degrees of freedom? What's a typical scale, right? At high temperatures, you treat them as free, but of course they cannot be free, otherwise nothing interesting would ever happen.
Of course.
So what's the expected scale?
Yeah, I mean, the scale we have, like, here, the scale that we extract is something, okay, so what we can say is that, okay, these remaining degrees of freedom are correlated, and the energy scale is, is about 8.5 Kelvin. That's all I can say. And if I compare that with my lowest, the temperature that I can measure in, like say, in heat capacity, I can safely say that I have frustration factor at about 80, right? Because it's pretty much like that. You cannot compare, I cannot say that my frustration factor is actually due to this high temperature revised constant that I got. It's not that. My frustration factor should be I must compare with this number here. But it still gives me a pretty high frustration factor for the system, right? But I cannot tell you which is the size of the interplane correlation and the in-plane correlation. Maybe now with single crystals I can do it, right? But we still have to work out as well the anisotropy of the magnetic interactions. We have some preliminary ESR results, but
but this is the scale. Okay.
This is the scale.
Okay, thank you.
Yeah, thank you.
Barium titanate is a room temperature ferroelectric. Does anything happen to the ferroelectricity in this
this is
substituted material?
Is there
any coupling to the magnetism?
Yeah, this is actually a very nice question, because all the story actually went back to when I was about to finish my PhD. So the whole idea was to get multiferroics, right? So we start mixing someone who is magnetic with someone who is ferroelectric, and then we, like say, use this very complicated structure, so you break inverse symmetry. So everything was there, but that didn't work out. So the properties, the multiferroic properties is not very good, but it turned out that the magnetism was more interesting. So I started looking at the magnetism. So if you take, for instance, the stuff as dielectric constant and so on, we actually don't see any. Actually, I must say that I stopped looking at that. As far as I know, Raimundo has a PhD student who is looking at that a little bit more closely, but as far as I know, nothing really interesting emerged so far. But that was our initial motivation to study this compound.
More questions, comments? No? So then let's thank all the speakers again.
Yeah.
Time for the picture now.